Assalamu alaikum. Welcome to the second class of the mechanical design of the overhead transmission line. We'll start from the summary as we have discussed in the last class that length of the conductor is denoted by small l or sometimes s is equal to L. L is the span of the towers into 1 plus W square L square by 24 H square. W is the weight per unit length. H is the horizontal tension which is occurring at the middle of the line or the minimum point of the line. Vertical distance is given by Wx square by 2h. This is actually the formula which can be used at any distance x from the origin or the minimum point. This is the sag that is given by d, that is equal to Wl square by 8h. So maximum tension is given by, that's T, that is the total tension, that is equal to h into 1 plus 1 by 2 factorial into Wl by 2h whole square. So we'll be using these formulas to calculate different quantities. So let us try to introduce one more parameter that is given by C. It is a ratio of the horizontal tension to the weight per unit length. So when we calculate the length of conductor in terms of C, so this formula is modified because sometimes I'm not going to usually use this C uh, in my lectures, but sometimes you may be asked or you may be given the value of C instead of H and W. So in that case, you can calculate the length of conductor like this. L is equal to 1 plus L square by 24 C square, where here C has been substituted for the ratio of H divided by W. Similarly, vertical sag can be given by this x square by 2c and the vertical distance, and sag can be given by L square by 2c. So this is how the different formulas can be modified by introducing the parameter C. So let us now discuss when the supports are at different levels, they're not the same level from the ground, how these equations can be used to find their minimum point or other clearances from the ground. So let us say again we are assuming that L, capital L, is the span the distance between the two supports, two poles. A and B are the two top points of the poles, and the conductor is hanging between these points A and B. Let us say this is the minimum point, or we can say this is our origin, and x1 is the distance from the point A from this O, horizontal distance we can say, and d1 is the vertical distance of this point A from this O. Similarly, x2 is the horizontal distance of this point B from this O, and d2 is the vertical distance of this point B from this point O. And we can see from this graph that this small h will be the difference of these two distances, that is d2 minus d1. Or from this you can see also this x1 plus x2 will be equal to L. Now rewriting the equation, that is y is equal to wx square by 2t. But in previous equation we have written that this vertical distance in terms of x is given by wx square by 2h. We can interchangeably use t and h because they are always very close to each other. So from here on, instead of h, I'll be using t for all the formulas. And I will show you how this t is, or how the h and t are very close to each other. So when y is equal to d1, this y is equal to d1, x is equal to x1. So we can write here d1 is equal to wx1 square by 2t. Similarly, d2 when y is equal to d2, x will be equal to x2. That is this equation. So in that case, this wx square by 2t will be equal to d2. And this h is equal to d2 minus d1, that is difference of d2. It will be equal to w x2 square minus x1 square divided by 2t is equal to h. That is what here it is written as w by 2t into x2 square minus x1 square. Also, as I told you that this L will be equal to the summation of x1 plus x2. So this will be equal to x1 plus x2. Now this equation can be written as, this is a square minus b square will be equal to a plus b into a minus b. I will write it as x2 minus x1 multiplied by x1 plus x2. That x1 plus x2 will be divided to this, or we can say when we take this 2t to this side, it will be equal to twice th divided by w is equal to x2 square minus x1 square. And when I factorize it, it comes out to be x2 minus x1 into x2 plus x1. I will keep x2 minus x1 here. It will be equal to twice th divided by w divided by x2 plus x1, that is equal to x2 minus x1. So this is that equation. So this comes out to be twice th by this h should be actually this small h, it should not be having the capital H. It is a difference of this d2 minus d1, so don't confuse it with the horizontal component of the tension. This is the small h, that is the height difference. So this x2 minus x1 is equal to twice th divided by w, x1 plus x2, and we know that x1 plus x2 is equal to L. So this x2 minus x1 is equal to twice th divided by wl. So from these two equations, we can calculate the value of x1 and x2 in terms of LT and H and W. So when these two equations are added, you can see that x1 and x1 will cancel out, and this will be 2x2 will be equal to L plus twice th divided by WL. That means x2 will be equal to L by 2 plus ht by WL, and 2 is divided. Similarly, when this equation is subtracted from this equation, you will see that x2 and x2 will cancel out. X1 minus minus plus x1, that will be equal to twice x1 will be equal to L minus twice th WL. When you subtract by 2, then x1 will be equal to L by 2 minus ht by L. So from these two equations, we can get x1 as well as x2. So x2 will always be positive because we have a plus sign over here and all the other quantities are positive. But this may have all the three values, whether positive, negative, or 0. If L by 2 is greater than ht by WL, then x1 is positive, and our figure may be like this. If L by 2 is equal to ht by WL, then x1 will be equal to 0. That means this origin will be at this point A. So origin would have been at point A. So in this case, in the first case, the origin will be in between the towers or in between the supports. If L by 2 is less than ht by WL, then x1 is negative. That means this origin may be to the left of this support A, and actually it will not be there because the curve will shift its or will change its trajectory after this point. But we can assume an imaginary part of this axis that might have this origin if we extend this curve to this side, and it will be to the left side of this support A. So that's what is written over here. If x1 is negative, then lowest point O of the imaginary curve lies outside the actual span as shown. That is shown here. You can see that these are the two supports, and if we draw it or if we extrapolate it, its minimum point may be over here, which is to the left of this support. So this may be x1 and L by 2 is less than ht by omega L or WL. In that case, the origin will be to the left of this one. So this distance will be d1 and this distance will be d2 again. From here to here, x1 plus x2 will be equal to L, that is this, because this is negative. X2 minus this quantity will be equal to this. Now coming to the effect of ice on the sag or on the weight of the conductor. The sag is determined for the span design at which the transmission line is constructed, so that the accumulation of snow or ice and excessive temperature change will not stress the conductor beyond its elastic limit. That may cause permanent stretch or fatigue failures from the continued vibration. This is very important because we need to design the conductor in such a way so that in the worst case condition there is not the damage of the conductor under the extreme conditions, or there may not be. If the conductor bears the tensile strength, it may not overcome the minimum clearance of the line from the ground. So these two things are very important to consider. In mountainous area, the thickness of the ice formed on the conductor is very significant. When the ice is accumulated on the conductor, it may result in the increase in the weight, and when weight is increased, it may result in the increased elongation or increased tension. That may increase the sag as well as increase the tension. So we have to be very careful about that. Accumulation of the air ice on the line conductor has the following effects on the line design. Increase the dead weight, that is the weight per meter of the line, and it increase the projectile surface of the line subject to the wind pressure. So uh, when the wind strikes on the conductor, you can see the available area for the wind when there is ice is more as compared to the without ice, and when the ice is accumulated on the conductor, its weight also increases, which results in the more sag. So this is the conductor. We are assuming a uniform distribution of the ice over here. So, or uniform accumulation of the ice over the conductor. Let dc be the diameter of the actual conductor and ti be the thickness of the ice over the conductor. Let us see both of these distances are calculated in centimeters. The cross-sectional area of the ice only will be the area of the whole circle minus area of the conductor. The area of the whole circle will be pi by 4. When we calculate it in terms of diameter, it will be pi by 4 into total diameter with ice will be equal to dc plus twice ti minus pi by 4 into area of this circle, that is pi by 4 into dc square. Taking this pi by 4 out, it's equal to dc plus twice ti square minus dc square. So when we open it up, it will be equal to dc square plus 4 ti square plus 4 ti dc minus dc square. This dc square and this dc square will cancel out, and we are left with 4 ti square plus 4 ti dc 4 for 4 ti square and 4 ti dc will cancel out with this 4. Then we are left with this pi ti square plus dc ti. Taking ti again outside, it will equal to pi ti into dc plus ti, and since both of them are calculated in centimeters, the unit of area will also be in centimeters. So when we convert it into meters, so area will be equal to pi ti into dc plus ti into 10 to the power minus 4 meters square. So volume of this ice will be equal to, actually since this is a cylinder, it will be equal to pi r square h or pi d by 4 square h. Since we have calculated area already, so or we can say A into h, where h is the length of this cylinder or height of this cylinder. We are assuming this height or length of the cylinder to be 1. So volume will be equal to this 1 multiplied by this AI, meter cube per meter per meter. So this volume will be equal to pi into Ti dc plus Ti into 10 to the power minus 4 meter cube per meter, because we are using only 1 meter of the length. So this is the volume. The total weight of the ice will be equal to volume of this ice multiplied with density of this ice. So that density of the ice is denoted by, or weight of the ice per cubic meter, that is the density of the ice, that is denoted by WC. When that is given, the total weight of the ice will be equal to this density multiplied by the volume that we have just calculated, that is WC into V ice. So that is equal to WC into pi Ti dc plus Ti into 10 to the minus 4. This will be the weight of the ice. And therefore total vertical load or vertical weight on the conductor per meter length will be equal to summation of the two weights, where Wt is the total vertical load on the conductor per meter length, W is the weight of the conductor per meter length, weight of the actual conductor, and Wi is the weight of the ice per meter length. So this is how we can calculate the weight of the ice and the total weight. So effect of the wind. In this case, we always assume that the wind blows uniformly and horizontally across the projected area of the conductor covered without ice or with ice. This is the wind force that we are assuming uniform and horizontally on the conductor without ice, and we are assuming that this is the uh, we can say side view of the conductor, where we assume that this wind is blowing inside of the page from my face towards this conductor or towards the page. So when this happens, you can see that this conductor or this wind faces this much of area, because we are only interested in 1 meter of the length. So from here to here, you can see the area will be equal to dc into L, the area for the wind which is available to strike will be equal to this area, because we're assuming this to be the side view, and from this side wind is blowing from my face towards this page, into this page. So that wind is facing this much of the area, as we are assuming L is equal to 1 meter, or if it is only L, then the area that is facing this wind, that is faced by the wind, will be dc into L. So the projected area per meter length of the conductor with no ice will be A and I equal to L, where A and I will be equal to dc in centimeters. So SNI is the projected area total without ice cross ANI is the cross-section area of the conductor covered without ice in square meter. So for 1 meter length of the conductor, this SNI will be equal to dc divided by 100 into 1 meter square per meter. So the total horizontal force exerted on the line as a result of wind pressure without ice. If it is given that a wind pressure is given in terms of small p, so the total force given by the wind will be equal to this SNI into P, where SNI is equal to dc by 100. It's only dc by 100 into 1, and P will be given in terms of kg per meter square. This should be small p, that's we have used over here. So F is the horizontal force due to wind pressure exerted on the line, and P is the wind pressure given in kg per meter square. So here also you can see that since this is in kg per meter square, we are multiplying this meter square by meter square. It is only meter, so we get total uh, weight due to wind will be kg per meter. So that is what we have to count. So with ice, it will be equal to SWI into AWI into L. So AWI, that is area. Now the area that's faced by the air or wind will be this total area. The total area will be equal to dc plus 2 ti into L. That's what given by, but L is considered to be 1. So SWI will be equal to dc plus 2 ti divided by 100 into 1 meter square per meter, or in terms of that will be only meters. So with ice covered, the wind force will be given by SWI into P, where SWI will be equal to dc plus 2 ti divided by 100, and F is equal to dc plus 2 ti divided by 100 into P kg per meter. So since the wind force we are assuming to be in the horizontal direction, and the total weight, that is Wt, is equal to W plus Wi, that will be definitely uh, appearing across this vertically. So the total effective weight that is appearing across this conductor will be the uh, we can say it is the vector sum of these two. So vector sum of these two will be equal to Ff plus this. That can be calculated by using the parallelogram law of this. Since they are vertical to each other, this We will be simply square root of this force plus this force, that is equal to square root of F square plus W plus Wi whole square. This will be the effective weight of the conductor, including the wind force and the ice weight. So therefore the sag will be equal to We L square by 8T, where W is the effective weight given by this formula. Now let us try to use the same formulas to calculate the total sag. A stress crossing overhead transmission line has a span of 150 meter. Over a stream, horizontal wind pressure is given by this. The thickness of the ice is 1.25 centimeter, diameter of the conductor is 2.8 centimeter, and weight is 1520 kilogram per kilometer, and the ultimate strength is 129900. Use a safety factor of 2 and 912 kg per meter for the weight of ice. Use a parabolic method, or you can use the same method. Determine the following: weight of the ice in kg per meter, total vertical load on the conductor, that is WT, W only, horizontal wind force exerted on the line, that is the W, that is F, effective load acting on the conductor in kg, uh, that is total weight WE, effective weight, and sag in meter. So first we'll calculate Wi. Wi, as we know, that is equal to WC pi Ti into dc plus Ti into 10 to the minus 4, and WC is given as 920 kg per meter cube. Ki is given as 1.25 centimeter, dc is given as 2.8 centimeter. So putting all these values into Wi, so Wi will be equal to this, that is 1.45 kg per meter. So this is for this. Total vertical load will be equal to this Wi plus W. Total vertical load will be equal to W plus Wi, that is 1520 kg per meter. So this can be equal, and Wi is equal to 1.45. This can be written in terms of meter, that will be 1.52 kg per meter, because for 1 kilometer it is 1520 kilogram, and for 1 meter you have to divide it by 1000. So this is like this. So total WT will be equal to 2.97 kg per meter. Similarly, F is equal to, with ice, dc plus 2ice Ti divided by 100 into P into P. So dc is given as 2.80, Ti is given as 1.25, P is given as 20 kg per meter square. So this is equal to 2.80 plus 1.25 divided by 100. So this 100 is actually converting this centimeter into meters. So into 20, it comes out to be 0.81 kg per meter. This is the total wind force, horizontal wind force. So the effective weight will be equal to square root of F square plus W plus Wi whole square. So F is 0.81 kg per meter and WT is 2.97 kg per meter. So when you use it, it comes out to be 3.078 kg per meter. So T will be given by ultimate strength divided by factor of safety. Ultimate strength is the strength or tension at which this conductor breaks. But factor of safety means we just want to limit this tension away from this ultimate strength depending upon the factor of safety. Since factor of safety is given to be 2, that means we are limiting this tension to this 12900 divided by 2, only 6450. The tension away from this, the more the tension away from this 129 and 0, the more is the safety factor. So for having safety factor of 2, so we have the tension only half of the ultimate strength tension. So since we calculate all these values for calculation of this D, so D will be equal to WE L square by 80. W is given by this, L is given 50, and 8 is from the formula, T is given as 6450. So this is the vertical sag of this conductor. Now, an overhead transmission line at a river crossing is supported from two towers of height 40 meter and 80 meter above the water level with a span of 250 meters. Weight of the conductor is given as 1.16 kg per meter, and the working tension is this. Determine the clearance between the conductor and the water level between the tower. This is very important. And this is, you can see there are two towers. One is at 40 meter height and there is 80 meter. That means they are not at the same level. We need to use the formula which are for the different levels. So we know that this x1, that is this x1, we're assuming just a minute, I just go back for this x1. This x1, we need to first calculate x1 and see whether this x1 is positive, negative, or 0 to find out the value, to find out the location of this point O. So x1 is equal to L by 2 minus ht by WL. So L by 2 minus ht by WL. So L is equal to 250. H is equal to the difference of the heights, that is 40 meters. 80 minus 40, and T is equal to 1800 kg. So when you put it there, W is equal to 1.16 kg per meter. So you get the value of x1 is equal to minus 123.2. So that means x is negative, the O is to the left of this point A. So then this means D1 will be equal to uh, when you draw a horizontal line from this point to this point, which is parallel to the this, I can say, Earth. So the distance between this point O and this point P, that's the vertical distance, is D1, and the vertical distance of this point O and this point B is D2. There should have been one more vertical distance given, that is point A and point O. I will try to manipulate that on my own. So the horizontal distance from point P and O, that is point P and O, this will be equal to, from this point to this point, it will be equal to this x1 plus the half of this. So that's L by 2 minus, that's half of this, minus x1. Since minus x1 is itself minus, it comes out to be plus. So it comes out 248.27. So the horizontal distance between this point B and this point O will be the total distance of this 250 plus this x1. So this comes out to be, you can see, 250 plus this x1, 373.27. Now D1 will be equal to vertical distance, that we are using the vertical distance Wx square by 2t, which is at a distance of this much OP dash from the origin. We can use that formula, that is W L by 2 minus x1 square, that is this, divided by 2t. It is equal to 19.87. That means this D1 is 19.87. Similar D2, that is W L minus x1 whole square by 2t. It is this distance. It comes out to be 44.9 meter. You can see from this to this, 44.9 centimeters. 44.9 meters, sorry. Actually, we can calculate this distance also, which is at a distance, horizontal distance of x1 from the origin. That will be equal to W x1 square by 2t. When you find out that W x1 square by 2t, where x1 is 123.27, you will get the value of 4.9. It has not calculated, but you can calculate on your own. So hence midpoint P is at a distance of is D2 minus D1. This point P is D2 minus D1 from point B, isn't it? Because this is D2, this is D1. So from point B, the vertical distance of point P from point B will be equal to D2 minus D1, that is 20, 25.04 below point B. And height of the midpoint P with respect to A, that is height of this with respect to A, that is this distance from A, will be equal to this distance minus this distance, that is 19.86 minus 4.9, that is this distance. So therefore clearance between the conductor and the water level at the midway between the towers will be, that is this height plus the distance between this point P, vertical distance between point P and point A, that is 40 plus 14.96, that is 54.96. Or you can see this height minus this distance. This height is 80 and this distance we have calculated 25.04. So from this also you can calculate this. This is 55.96 meters. So the clearance of midpoint from this ground level is this much. Now consider transmission line with the following data. Span length is 300 meter. Maximum allowable tension in kg in the conductor is 3500 kg. That is actually T. Weight of the conductor is 700 kilogram per kilometer. Calculate the horizontal component of tension, that is H in kg, for the transmission line. Given L is equal to 300 meter, T is equal to 3500 kg, W is equal to 0.7 kg per meter. When you calculate this in terms of kg per meter, you have to divide by 1000. So using the actual formula of tension, it's T is equal to H into 1 plus 1 by 2 factorial plus into WL by 2H whole square. So When you open it up, it will be W square L square by 2 into 2 square is equal to 8 H square. That is this. So putting the value of W and L, so you will get, and T, this T is 3500 is equal to H into 1, because we have to find out the value of H. 0.7 square into 300 square will be 8H. So if you directly solve it from your calculator, you will get 3498.42. And I have told you earlier that this T and H are very close to each other. We can interchangeably use them, whether T or H. Otherwise you can convert this to a quadratic equation. When you simplify it, this will be 8 square plus this much. When you calculate it, it will be 44100, and H and H will cancel out. And when you open it up, this 8 and 8 will cancel out. And when you divide by 8, it will be 5512.4. This will remain only H square. 1H will be multiplied to this. It will be 3500H. So changing it to quadratic equation and solving it is again giving the same value, 3498.42 kg. Here again you will see that both of T and H are very close to each other. Now there is some more design problem. One is that EO-line vibration or resonant vibration. Overhead conductors will subject to a normal swinging in wind, and apart from that may subject to a vibration known as AO-line vibrations or resonant vibrations. These AO-line vibrations have low amplitude of the order of 0.5 centimeter or so, and high frequency, is 50 to 100 Hz. These are caused by the vortex phenomena, or we can say whirlpool phenomena, in the low wind speed of 10 to 30 kilometers. So these type of vibrations can be omitted or reduced by using a stop bridge damper. It is actually a steel rod at the ends of which we have two masses connected, and in between it is connected to the actual conductor like this. So these are used to reduce the airline vibrations or resonant vibrations. The length of the typical damper is about 60 centimeters, that is from here to here. This is actually a stock bridge damper. The weight of this topic damper is around 5 kg or more. We have one more type of this vibration, that is galloping or dancing of the conductors. These vibrations are of low frequency from 0.25 to 2 Hz and the high amplitude, that is up to 6 meters. And they are generally caused by the asymmetrical layers of ice formation. These vibrations are self-excited type. They are uh, usually caused by the asymmetrical layers and by the standing of the conductor. They can be reduced by using the horizontal configuration. Otherwise, they are very difficult to reduce. We should try to minimize them as possible as we can. Otherwise, they also may reduce in the so they may result in the flash over the lines, because when this type of thing happens with the conductors may swing and they touch with each other and may touch with each other, and there may be a complete shutdown of the line. Now one more thing is a stringing chart. This is also an important chart regarding the sag and tension. It it is actually These are actually the curves of tension and sag versus temperature, and they will tell you how the sag and temperature tension will change as the temperature changes. Because when temperature changes, the conductor elongates, sag will increase, and tension will decrease accordingly, and the tension and sag curves will change like this. So such type of chart or graph of sag and tension with respect to temperature are known as stringing charts. These are very useful while erecting the transmission line conductors for adjusting the sag and tension properly. Because when you have such type of uh, stringing chart available for you, and while you erect a transmission line where in any area, and in that area you know that you have to first find out the minimum temperature and the maximum temperature, and by selecting the minimum and maximum temperature over here, you can accordingly design a transmission line for the maximum sag and minimum tension. So by having that, you can use this type of chart to first finally select the height of the towers. For example, if you have calculated that for the worst case condition for this type of, let us use an example, this type of a system, we have a sag of 0.7 meter. So here you can see that the minimum clearance should be equal to 5.2. That means the height of the tower should be equal to 5.9 meters. Similarly, for anyone, if for this case we have a sag of 1.2 meter, so the minimum height of the tower should be equal to 8.8 plus 1.2, that is 10 meters. So this chart will help us in designing the transmission line tower height. Okay, thank you. Today I will stop over here.